introduce to you a big idea in the topic which is called entropy. And we're going to look here at, can the entropy change tell us whether a reaction will be feasible? And probably you're now thinking at this point, what is entropy? So here we are. Entropy has got a symbol which is S. I don't know the origin of that, but it is S. But entropy change is delta S. Okay, the same as enthalpy change delta H, but we're going to see that we can actually have absolute entropy values. So you can say to me, what's the entropy of water at 25 degrees C? And I could tell you. If you asked me what the enthalpy of water is at 25 degrees C, I couldn't tell you. We can actually measure entropy S values, and you're going to use them before the next hour's up. So what is entropy? This is the textbook, the specification, I think definition, certainly the textbook. It's a measure of the dispersal of energy in a system. Or I'll put in there the spread outness. So the more ways there are to spread energy out in a situation, the more entropy that there is. So the more that you can make energy be spread out, the more entropy there is. So the first one was, which has more entropy, many particles or few particles in the container? Now, interestingly, this one was very divided. We had 19 people saying many particles gives you more entropy, and 33 giving you fewer particles. Let's see what's right. The correct answer is many particles. Now, I wouldn't necessarily write down the stuff in the yellow box, because you can always have a look at it later on the PowerPoint that you've already been sent on this. But what does it say here? More particles means the energy can be spread out among the particles. So, for example, just to show you, if I've got, say, for example, 2 units of energy, so 2 units of energy, here they are, my 2 dots. Okay, there's my 2 units of energy. If I've got a situation where I haven't got many particles, let's say I've got 2 particles here. Well, I can spread out, I can either give one particle both the dots of both the units of energy, or I can give the second particle both units of energy and the first one nothing. Or the third option is I can give them one each. So there's basically only 3 ways to spread the energy around. Now let's say I increase the number of particles, and now I give myself 5 particles. I've still got 2 units of energy. I can give the first one a unit of energy, and I can give the second one a unit of energy. Or I could go for a unit of energy to the first and the third. Or I could go for the first and the fourth. Or I could go for the first and the fifth. Or I can give 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, and so on and so forth. So I've got here more ways to spread that energy around. More ways to spread energy, more dispersal of energy, more entropy. So more particles you have, the more entropy that you've got. The second one, this one was pretty, it was 4 people thought that confining the particles gave you high entropy. Most people, 49 responses, said that the particles would be spread out to give you higher entropy. And that's true. The energy is spread over a larger space with more space for the particles to occupy, and therefore you have more entropy. Next one is about the ways the particles can move. I've put, in fact, everyone got this correct. If you can move, particles can move in many ways, then you have higher entropy. And the final one was about energy. A high energy situation does indeed have higher entropy. 44 of you put that, that's correct. So the more energy you have, the more ways you can spread it out. So think about if you have very, very little money, then you can pretty much, there's only point in having, if you have very, very little money, then you have to spend it all on one thing. If you've got lots and lots of money, you can divide it between lots and lots of different, say, investments or something like that. So the more energy you have, the more ways you can spread that energy around, the more entropy that you're going to have. So now I just want to summarize this by saying that the most common popular concept for entropy is this idea of order and disorder. So ordered states have energy concentrated in one place or one type of motion of particles. So for example, they're all vibrating. And so they have a lower entropy. Whereas disordered states, they're going to have the particles moving in many, many different ways. They're probably also going to have the particles being more spread out. Those tend to have higher entropy. So high entropy is all about disorder. And I put a summary on here for you to think about. So it's a measure of dispersal of energy in a system. So the more spread out or more ways to spread energy out, so the more ways you can spread energy out, or the more disorder you have, the higher the entropy. Now, at the moment, this is still pretty abstract, but we're going to gradually bring it down to the ground by thinking about how does entropy change when you have different states of matter. Okay, and actually, interestingly, looking at your responses, by far the most popular response was that gases had more entropy than liquids, which had more entropy than solids. The other second most popular response was that the solid and liquid will have about the same amount of entropy, but a gas will be much bigger. And in fact, that is exactly the right kind of intuition. So if I show you a graph here of entropy versus temperature, it shows us two striking things, and I'll take them in turn. So firstly, there is a general increase in entropy with temperature. That's the first point to note about this graph. So if particles have more energy at higher temperatures, it's going to be spread out in more ways. And so we get this general increase in entropy. At the same time, we see here that when we get to these particular temperatures here, this temperature here is the melting point. And when we get to the melting point, the entropy jumps up. And this is the entropy change between a solid here and a liquid up here. We can see that there's this gap in entropy here, the so-called entropy of fusion, it's called here. So the entropy of a liquid is bigger than the entropy of a solid because you've got more freedom of movement or more disorder when you go from a solid to a liquid. And it's the same story when you get to the boiling point. When you get to the boiling point, you again have this sharp change in entropy, the entropy of vaporization. Because when you get to being a gas, you can now start to move really, really freely. You can move in any direction. You can rotate around. You can move quite quickly. You've got more energy. Whereas in the liquid state, you're still pretty confined, quite close together, but you can maybe sort of roll over the top of that guy or move down there. In the solid, everything's very ordered in a lattice, and all things are doing is just vibrating a bit. So solid, less freedom of movement, very ordered, low entropy. Liquid, a bit more freedom of movement, a bit less ordered, higher entropy. And gas, lots of freedom of movement, lots of disorder, lots of entropy. Lovely, right, we'll move on. So first thing we're going to do is just look at predicting entropy changes qualitatively. So we're going to look just at how we can predict, will it be an increase in entropy or a positive delta S, or will it be a negative delta S, a decrease in entropy? We'll go on to quantitative predictions a little bit later on. So firstly, predicting entropy changes, and we're talking here qualitatively. And you're basically going to get two types of questions on entropy. The first will be a qualitative, and then there's a quantitative, actually a calculation of delta S. And actually the quantitative is actually easier. But here we're just looking at trying to work out the sign of the entropy change. So is delta S positive or negative? And what I counsel you to do in this is take two steps. The first is to write out the equations for the process, and you must include state symbols. And the second is to decide whether reactants or products will have higher entropy based on the state of matter, number of particles present, etc. So I've got three examples for you here. First reaction everyone looked at was the water from liquid to gas. And you're absolutely right that here we are going to have delta S is going to, or entropy is going to increase. And the reason for that is we've got a gas being produced from a liquid, and a gas is more disordered, and therefore it's going to have higher entropy. Second one was this reaction here between calcium carbonate and HCl, and the vast majority of 96% of you got this right. You said again that the entropy here is going to increase. And the reason for that is, again, we're looking at solid, aqueous, and then crucially a gas. So basically, if you've got something that doesn't have gas going to gas, we're going to have an increase in entropy. For the same reason as before, gases, more freedom of movement, more ways to spread the energy, more disorder, more entropy. Now this one here was a little bit different. This one only, no, 91% of you got this right. Which is that actually entropy does decrease here. And here we've got all gases, so we can't use the states of matter. What we can do here is calculate that we've got 4 molecules on the left-hand side and 2 molecules on the right-hand side. So if we remember back to our starting point, was that the more particles you have, the more ways you can spread the energy out among them, the more entropy you've got. So this 4 molecules is going to have higher entropy, and 2 molecules is going to have a lower entropy. And so in this case, entropy is going to go down. Now the final one was just there, really, that I've taken that from an exam question actually. And all I've done is just to show you that there are actually lots of ways to get the mark. In fact, those first 6 responses that were all correct are all valid options on the mark scheme. You can talk about order or disorder. You can talk about freedom of movement. You can talk about dispersal of energy. But if you want to get the mark, you have to actually link it to the equation. And looking especially at the state symbols and the number of species. Now, about 6 of you got the last one you put. You said that there are more products than reactants, and that was a reason for an increase in entropy. That you've got to watch, because remember, in an aqueous solution, these ions will be separated. So you've got Ba2 plus, you've got NO3 minus, and you've got another NO3 minus. Same with this one. You've got Na plus, and there's two of them, and you've got SO4 2 minus. Whereas on this side, this is a solid, so you've just got a single particle there, BaSO4. And here you've got Na plus and NO3 minus. You've got two of both, so you're going to have 2 and 2. So if we think about this purely in terms of numbers of particles, we've got 6 on the left and 5 on the right. It's just that this full equation is actually obscuring that. But again, the key to getting this one right is to having a look at that state change.